Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the second one in a series on constant angular speed in circular motion and looks at acceleration. Consider a particle at two different points in its motion. You'll see that in the first position the velocity is directed along the tangent, of course, and it's in a different direction from what it is in the second position, even though the speed is unchanged. Now that has to mean, since velocity is a vector, that it's got an acceleration. Now the form of that acceleration requires quite a careful analysis, and I'm simply going to quote the result here. The object certainly has an acceleration, and what we can say about it is that it's directed towards the centre of the circle, and it's related to the radius and angular velocity by one of those two formulae, which are alternatives, one for the other. Note that if the speed is constant, which is what we're assuming at this stage, the tangential acceleration is non-existent. We can take it as zero. So let's use those two formulae which you see listed at the top of the slide in context in this particular problem that comes next. You'll see that I've marked the acceleration directed towards the centre, parallel to the radius, and that's the direction which accounts for the change in velocity as the constant speeding particle moves round the circle. So we ask here, what's the acceleration of the object? Well, the first pitfall is to realize that we've got non-standard units prescribed here. 36 kilometers per hour won't do, 36 won't do for v. So our first step is to express v as 36,000 meters divided by 3,600 seconds. At that point we'll have the speed in the correct units, which is meters per second, which is obviously in this case 10. So if v is 10, what can we say about a? A is given by the formula v squared over r. So we're going to have 100 for v squared divided by 20, which is the radius value r. So that gives 5. Hence we can say that the acceleration is 5 meters per second squared. So there's the calculation repeated, perhaps a little more clearly, and there's the conclusion in context. The acceleration is 5 meters per second squared, and note we must specify that it's directed towards the centre of the circle. Right, now let's look at some context for this. Here we've got a female hammer thrower. What's she trying to do? Well, an idealization of what she's doing will be that she's trying to get the hammer to move in a circle. She's getting it to try and go faster, so it's accelerating not just towards the centre but also along the tangent. But the point is that at a certain moment she's going to let go. Now when she let goes, surprise surprise, the hammer doesn't continue in the circle. Now that should bring out a reinforcement of the idea just explored about acceleration. You can see that in order to stay in the circle, it has to have an acceleration, because as soon as you remove the force, which is the tension in the wire, creating the acceleration so that it no longer exists, the hammer shoots off in a straight line, as Newton says it should. Well, it's a straight line to begin with. Of course, gravity soon makes an impact on it. Gravity soon makes its influence felt, and it will move towards the Earth. So basic idea there is twofold: that there is an acceleration towards the centre for circular motion, and that it must arise from a force, in this case the tension in the wire. And in succeeding videos we'll be looking at that kind of connection in much more detail. Newton's law tells us that an acceleration occurs when there is a resultant force. So what does this mean for circular motion? Well, it means that there must be a resultant force acting on the object if it's to move in a circle. And that force must be in the direction of the acceleration. And if we're agreed for the present that we're talking about motion in a circle with constant speed, then the direction of that force must match the direction of the acceleration, which is towards the centre. That concludes this video presentation. The next in the same series will be about further motion, and this time motion in a horizontal circle, where we consider the forces that are acting. I hope to be with you later to explore that.